All right, welcome back to the Explainer. Today, we're going to dive into one of the most versatile, most fundamental building blocks in all of modern electronics, the operational amplifier, or as most people call it, the op-amp. We're going to break down its core principles and show you just how this tiny component powers so much of the world around us.
So, have you ever wondered what the secret ingredient is that powers everything from your guitar amp to complex medical devices? It's a component that's so common, yet so powerful. And the craziest part is, its behavior is governed by just two super simple rules. Well, it's the operational amplifier, or op-amp for short. And you'll see it everywhere, usually represented by this simple little triangle symbol. But seriously, don't let that simple look fool you. Inside that triangle is the power to perform mathematical operations on electrical signals. So let's start by looking at how it actually connects to the world.
Okay, so to really get what an op-amp does, we first need to understand its connections. It's got 5 key terminals that basically define its entire operation.
So here they are, the big 5. You've got 2 inputs, the inverting input, that's the one with a minus sign, and the non-inverting input with a plus sign. Then, of course, there's a single output. And finally, it needs juice to work, right? So it gets that from the positive and negative power supply terminals. And believe it or not, these 5 little connections are all we need to build some absolutely incredible circuits. Okay, now for the really cool part. To figure out what an op-amp circuit is doing, we don't have to worry about the dozens of transistors packed inside. Instead, we can just use 2, let's call them golden rules, that describe how a perfect, ideal op-amp behaves. There is one catch, though, a really important one. And that condition is something called negative feedback. All this means, really, is that there's a path, a connection, from the output terminal right back to that inverting input. This feedback loop is what lets the op-amp constantly adjust itself, keeping everything stable and predictable. And as long as that feedback loop is there, our 2 golden rules are good to go. All right, golden rule number 1, the voltage constraint. You might hear this called a virtual short, which sounds fancy, but here's what it means. The op-amp will do whatever it has to with its output to force the voltage at the inverting input to be the exact same as the voltage at the non-inverting input. You can almost think of this as the op-amp's number 1 job in life. And rule number 2, it's just as straightforward. Basically, 0 current flows into those input terminals, none. And why is that? Well, in an ideal world, the op-amp has infinite input resistance. It's like a perfect voltage sensor. It can read the voltage without drawing any power from the circuit. And that's it. Those 2 rules, that's all you need to unlock almost everything. So that's the theory. But how do these rules actually play out in the real world? By putting them to work, we can create a whole catalog of incredibly useful circuits. Let's take a look at a few of the most common ones, kind of like the amplifier's greatest hits. First on the set list is the inverting amplifier. And yeah, the name pretty much gives the game away on this one. So what this circuit does is it takes your input signal, literally flips it upside down, inverts it, and then scales it up or down. But here's the best part. You have total control. How much it gets scaled, we call that the gain, is set by nothing more than the ratio of 2 resistors that you get to pick. It makes the whole thing super predictable and super useful. Okay, but what if you want to make a signal bigger without flipping it on its head? Well, for that, you've got the non-inverting amplifier. Just like the name says, this setup gives you a bigger version of the input, and it keeps the polarity the same, no flipping. And once again, the gain is all in your hands, set by those simple external resistors. Total designer control. But op-amps aren't just about making signals bigger or smaller. Nope, they can actually do math, which brings us to the summing amplifier. This is where that operational part of the name really starts to make sense. What it does is it takes a bunch of different input voltages, literally adds them all up, and spits out a single signal that's the inverted, scaled sum of everything you fed in. Think about it. This is the core idea behind every single audio mixer on the planet. All right, so we can scale, we can invert, we can add. What's missing? Subtraction. And that is exactly what the difference amplifier is for. Oh man, this circuit is fantastic. It looks at 2 different inputs and is incredibly good at ignoring anything that's the same on both of them. We call that common mode signal, and a lot of the time that's just noise you want to get rid of. So it throws out the noise and only amplifies the actual difference between the 2 signals. So powerful.
And we even have a way to measure how good it is at this, called the common mode rejection ratio, or CMRR for short.
Okay, so we have to talk about something. Those two golden rules we've been using, they're for a perfect, ideal op-amp. They make the math super clean, and they're absolutely perfect for getting a design started. But the real world is, a little messier.
Let's do a quick side-by-side. Our ideal model assumes infinite gain, infinite input resistance, and zero output resistance. Just perfect numbers. A real-world op-amp gets really, really close. It's got incredibly high gain and input resistance and super low output resistance. But they aren't actually infinite or zero. The good news is, for most things you want to do, the ideal model works great as an approximation. But it's something engineers always have to keep in the back of their minds.
And really, that's the main takeaway here. The ideal model isn't wrong. It's an incredibly powerful tool. It's a simplification that lets us understand things. It lets us figure out how a circuit is going to behave pretty quickly without getting totally lost in the weeds of tiny real-world quirks.
So there you have it, a simple little component governed by just two little rules that can be wired up to scale, sum, and even subtract signals. It really is like the fundamental Lego block for all of analog electronics. So the real question I'll leave you with is, now that you know the rules, what could you build?